Welcome again for another. Hi, it's week 5. My gosh, I'm so excited yet again to be hanging out with you all to do yet another virtual astronaut challenge. We do have yet another big week that's come on up, and really glad to have you wherever you are joining right across Australia. Now, before we get going, I'm hanging out with you. I am on Western Sydney land, on Darug country. I really want to acknowledge the traditional custodians of the country I'm on, Darug country, and also we're connecting to all sorts of places right across Australia and beyond, everywhere, right across the world too. And I want to acknowledge all Indigenous custodians from various lands from where you are. I want to pay respects to our elders, past, present, and emerging. And I want to extend a real g'day to any Indigenous people hanging out with us today. We do have quite a session today. I know we've gone up to week 4, but hey, it's week 5 now, and we are now looking at the iteration and evaluation of your project, and we've got some very special guests as well. So, Jackie, is it right if we could just go to our current people, if we could, to sort of work out who we've got here. We have Scott. If I may, could you please say good day, and we'll see what you've been getting up to lately.
Morning, everybody. Coming to you from Wanneroo land in the beautiful Hunter Valley. I am absolutely stoked about what we've got for you today, and I'm going to be interviewing the amazing Dr. Carl and introducing the equally amazing Dr. Adrian Brown today, so stay tuned.
Thanks so much, Scott. And now we've got all those grey screens out of the way. Dr. Carl, amongst all the things that you do, I really love the work you've done with belly button fluff.
That was amazing. And in fact, I was able to work out what causes belly button fluff and why it's almost always blue. What causes it? Well, it's a mixture of fibers of clothing, dead skin cells, and fibers of hair, all held together by the dead skin cells. And why does it end up in the belly button fluff? In the belly button, because all hairs on the abdomen point to the belly button in the same way that all roads lead to Rome. And Harvard University showed me so much respect that they flew me to Harvard and provided accommodation entirely at my own expense. They wouldn't insult me by offering me money to cover it. That's how highly regarded the Ig Nobel Prize is.
I love it. I love how science can take you anywhere. Who would have known it can take you down into belly buttons? That's awesome. Hey, we also have Dr. Adrian Brown. Adrian, would you like to say g'day?
G'day, Ben. G'day, everybody. I am a NASA scientist in Washington, D.C., and I work on the Mars 2020 project, which is about 9 months into its voyage on Mars. And eventually we'll be returning samples from Mars. And this behind me is an image of our landing as it happened 9 months ago.
Fantastic. Really looking forward to what you can share. What we're about to discover with new research coming on in. And Alan, we've hung out with you before. We've learned a bit about business innovation. How's your morning been today?
It's absolutely fantastic. Thanks, Ben. And it's great to be here again. I'm coming to you from Camaragal country, from the Eora Nation, which means I'm sitting in Crow's Nest, Sydney. And I look forward to chatting to everybody. Thanks, Ben.
Thanks so much. Now, so a little bit north of that country is Kylie. Kylie Burrett, would you like to say hello, please?
Hi, everyone. It's fantastic to be here with you today. And I've got the amazing Glennie D with me. And we are coming to you from Wabakal country here in Newcastle. We'll be looking at some designs coming straight out of the classroom today with some fabulous questions for our expert panelists. So we are super excited and keen to dive in, and we'll have a shout out later on to some of those schools. So keep watching.
Really looking forward. Let's keep traveling further north. Wendy, tropical North Queensland, how is it today?
Hi, everyone. Here I am in Townsville, North Queensland, land of the Wulgarukaba and Bindal people. It is getting hot, but I just want to say happy National STEM Day next week. Today's lesson, though, we're going to take your thinking to a whole new level.
Yeah, absolutely. That's very true. And someone who does a lot of thinking is Ian down in the south. How are you doing there today?
Yeah, doing well, Ben. Hope you're doing well also. I'm coming from Griffith in New South Wales, Wiradjuri country. home of the New South Wales Virtual STEM Academy, and I'm really looking forward to seeing some of the questions from students of Murrumbidgee Regional High School being posed to Dr. Carl. So I know there's lots of kids out there watching, and today is going to be absolutely fantastic.
Thanks so much. So with all those introductions done, let's kick off week 5. And Scott, we have a lot of questions have come in from schools all over the country for Dr. Carl to really talk to. So Scott, what's going on there?
Oh, look, Dr. Carl is amazingly offering his time again. He's a great friend of the New South Wales Department of Education and tirelessly gives his time. But Dr. Carl, I just want to sort of do a bit of an introduction because he absolutely loves science, and he's been spreading the word of science on TV, in print, on radio. If you're a Triple J fan, you would be well aware of his work. And he's been doing that for 30 years now, almost as old as me. So also, I don't know if you're aware of this, but he's the author of 47 books. Amazing, 47 books. Imagine, I can't even imagine reading that many books. There's one behind me here. And he has been a student himself. So we're all students here, but he has been a lifelong learner. So think about this. He has degrees in physics, mathematics, biomedical engineering, medicine, and surgery. He's worked as a physicist, a labourer, a roadie for a band, a car mechanic, a filmmaker, a biomedical engineer, a taxi driver, a weatherman, and an actual medical doctor in a children's hospital. What an amazing career. And we're just so lucky to have him today. And he's going to answer some questions that are posed from some of the 6,000 students that are involved in this program. Amazing. And we're going to start off with, as Ian has suggested, a question that's come from Laura from his school, and cue video.
Hi, my name is Laura Wepler and I'm in Year 10 at Murrumbidgee Regional High School in Griffith, New South Wales. My question is, could we make chemical reactions in the air with greenhouse gases to take them out of the atmosphere? And how big a scale of reaction would be needed to make a difference?
Laura, yes. Message of hope here. We can both stop and reverse rising carbon dioxide levels and climate change and bring conditions back to what they were before you were born. Can we do it with chemical reactions? Yes. Remember the unofficial motto of the US Air Force, which is with enough energy, you can do anything. And pigs can fly. So you can do that. And the trick is to find the more efficient ways. So trees are really good at doing it. And there are many, many ways to pull carbon dioxide out of the atmosphere. This is called carbon sequestration. The methods that we're thinking of at the moment range from fully military industrial, where you just get a big machine and you throw electricity at it, all the way to biological, like growing plants in the ocean, and everything in between, including biochar. And yes, there are many, many ways that we can do it. And we have the technology to do it now. We can fix 90% of global warming simply by keeping fossil fuels in the ground. And then we have to start adding to nature, which will pull the carbon dioxide out of the atmosphere. And we just add to that. And we can bring conditions back to what they were before you were born. The message of hope. Go to the website drawdown.org. drawdown.org, and they deal with a whole bunch of different methods. Happy reading for a couple of hours there.
That's awesome. We've also got a question here from Beatrix, which is a Year 5 student from Ruxton Girls School in Melbourne. So we're coming from all over Australia today. And this one's a really interesting one to me because it really sets the scene for what we're doing on the moon. And which has been a big part of this project and about being able to grow food, because to grow food, we need water. And the question is, does ice or water on the moon have different properties to ice and water on Earth?
We'll find out when we get there, but almost certainly yes. Now, you think of water existing in three states. There's that invisible gas called steam, traditionally above 100 degrees C. Then between 100 and 0, you've got this liquidy stuff. And then from 0 down, you've got this thing which is just called ice. It turns out that there are at least 19 different crystalline forms of ice. Let me explain. Suppose you've got a totally square, cubic cardboard box. Boom, cardboard box. And you put one molecule of water on each corner. 1, 2, 3, 4 at the top, and down the bottom, 1, 2, 3, 4. That's called a cube, and that's called a corner cube. Now, suppose that you keep those 1, 2, 3, 4, 5, 6, 7, 8 molecules of water there, and then you shove another one in the middle. That then floating in the middle of the body, that becomes a face-centered cube. And then if you add a molecule of water on each face, and there's 1, 2, 3, 4, 5, 6 faces, you then end up with a face-centered cube. There are 19 different phases of water. And if you cool down water quickly, you'll end up in one of 3 different crystalline shapes. And if you cool down slowly, you get another 3. And there are just so many more depending on how you do the cooling and what's happening. The most common form of ice is called ice 1H, H for hexagonal, and it has tiny amounts in it of ice 1 cubic called H1C. And then there's 19 or 17 other different phases. So will we find different ice? Yes, we're learning so much about water. Will we be able to use it? Almost certainly.
That's awesome. I've done a lot of work in metallurgy, and those terms, when they talk about the crystalline structures with metals, is very similar too. So I wasn't aware that ice was acted in the same way, Dr. Karl. So I'm learning some great things today as well. Next question is from the Junction Public School, which is going to feature a bit today. They've been doing a lot of work in the AVA program, and thank you for being involved. But this one's a really cool question too, and it's something that I would like to get involved with in the future. So what are your views on this? Will there ever be a space hotel or resort on the moon, Dr. Karl, is the question from Alicia.
Once again, with enough energy, a pig will fly. So we are heading that way. We do have to become a space-going race for the following reason. We've got to preserve the human race. On Halloween, 31st of October in 2015, a rock 0.6 of a kilometre just missed us, and had it impacted with the Earth, it would have killed between 10 and 70% of all humans, depending on whether it landed in the dead heart of Australia, the Pacific Ocean, or a supervolcano. Had we had 3 years warning, and had it been on a impact collision course, we could have pushed it aside. We didn't have 3 years warning; we had 3 weeks. So part of us becoming a space-going race is having accommodations, habitats, hotels, call it what you will, all through the solar system. And the moon's really good. We're very lucky to have such a convenient place so close to us, and with a decent gravitational field, roughly 1/6 of our own. So the health issues are not too major.
Awesome. Next question again is from the Junction Public School, and this is a big call out to Alice, because Alice actually wants to be an astronomer for NASA when she grows up. But Alice, don't forget, there is an Australian Space Agency, and there are jobs that are coming. So in the future, you may be able to work for the Australian Space Agency as well as NASA in the future. And of course, we've got Dr. Adrian Brown, who's an Australian that's working for NASA right now. So an aspiration which is definitely available. But her question is, does the moon have lava tubes? And if it does, could you live in them?
Well, read the series by Fred Pohl, Pohl, and this is a whole series of science fiction books, Gateway, I think they're called Gateway, and what it says is that there are, this science fiction book, lava tubes on the moon In other words, where there was volcanic action and then the lava flowed away, but it cooled at the surface, leaving behind these tubes underground. And you can see them in various parts of Australia, including Cairns, from Cairns. And then when we humans go to the moon, we find alien spaceships there. Read on for the rest of the science fiction story. Did the moon have enough volcanic activity to do so in the early days? Unfortunately, I don't know. Now, somebody who would is somebody who's coming on later, Dr. Adrian Brown, who actually is inside at NASA. And so he might know more, or he might not, about the planetary geology of the moon, whether there was enough volcanic activity to have lava tubes. And by the way, I was reading an article yesterday which said that it were black holes to go and hit the moon, they would just burrow straight through, leaving behind a hole, which is not a lava hole, and it's not science fiction, but it's a different thing again. Answer, don't know.
Awesome. We've got a video question again from the wonderful Murrumbidgee Regional High School. Big call out to that, one of the leading STEM schools in Australia. And it's from Digby Jones. So cue video.
Hi, I'm Digby Jones. I'm in Year 8 at Murrumbidgee Regional High School, Griffith, New South Wales. My question is, what is dark energy?
Dark energy is real, and Brian Schmidt, who's the Vice-Chancellor of the Australian National University, shared a Nobel Prize for it a few years ago. Dark energy, if you turned into mass by E equals mc squared, accounts for 70% of the mass of the universe. We know it's real, what it's doing, and it began about 5 billion years ago out of the age of the universe of 13.8. 5 billion years ago, the fabric of space-time began to accelerate faster and faster and faster, and it's still doing it now. And this is caused by something that we call dark energy. We know that the expansion began then, this extra expansion, and it's going faster. We don't know where it'll end up, and we definitely right now do not know what dark energy is. But just for you, Dr. Digby, here's a prediction. By the time we get to the end of this century that we're in now, and remember, predictions are very difficult to make, especially about the future, your kids or nephews or nieces or family members at the end of the century will be playing as a toy, under the age of 10, with one of the following things: the missing 8 dimensions of space, dark matter, dark energy, or a black hole. And you'll say, Digby, now come inside and eat your lunch and stop playing with the black hole and stop playing with the dark energy. Anyway, that's my prediction. Could be wrong.
Nice. I really love this question. I've got a question here from as an anonymous person, actually. But how large would a bucket of water have to be to put out the sun?
The trouble is, it might actually help the sun keep on burning. You see, the sun doesn't do chemical burning. Think about atoms. Atoms have got a very small, dense core, microscopic, and then supposedly lots of empty space, and then electrons on the outside. Most of the energy that we get from human activity comes from chemical energy, where you get one atom and another atom, and you swap the electrons around. Carbon plus oxygen gives you carbon dioxide plus a lot of heat. The sun does nuclear burning, and every second it burns 620 million tonnes of hydrogen. Not 620 tonnes, 620 million tonnes. Now, it's at a temperature of around 15 million degrees, and what you're going to be doing if you tip in larger and larger amounts of water, you're going to be tipping in hydrogen atoms, and they'll be fuel for the nuclear fires. You'll be giving it more fuel. The trouble with the sun and why it's going to go out eventually or change state is it's going to run out of nuclear fuel. So if you chuck water onto the sun, that's kind of like throwing petrol onto a chemical fire. So it wouldn't make the sun go out, it'd actually make it live longer than its projected 5 billion year span, where it expands out to a red giant and then shrinks down to a white dwarf roughly the size of the Earth. Sorry to break your heart.
Amazing. We've got a question here from Thomas. Now, it only says CHAC, so I'm not sure where that is, but the question really goes, I think, to what we're going to see from Dr. Adrian Brown later on. He's got images of Mars, and we see Mars as like being very rocky and dry compared to the Earth. And The question that he has is that why are a lot of planets like this? Why are they so rocky and dry compared to Earth?
This is a complicated thing. It turns out that firstly, that we have discovered lots of other planets outside our solar system. The ones that are rocky like Mars, there's one of those in our solar system, which is Mars. And then there's Venus, but it's very, very hot. And then Earth is sort of like about 1/3 rock and 2/3 ocean. The rest of the planets in the solar system, and Mercury is rocky as well. So when they're getting further out, they're turning into gas giants, Jupiter and Saturn, and then ice giants. Now, here's a weird thing. We started really finding planets outside our solar system with Kepler, and we discovered maybe 3,000 or 4,000. Now, here's a really weird thing. The most common form of planet we've discovered does not exist in our solar system. It's a planet called a super Earth, somewhere a few times bigger, somewhere in size between a few times bigger than Earth all the way up to Neptune. And we don't have any of those in our solar system. So we're still trying to understand planetary evolution. The old one was that the planets all formed in the early days and they condensed out of this cloud of gas, and then the sun fired up, and then it started blasting out radiation in all directions, a solar wind, 1 million tons of charged particles every second. And so it blew away the atmospheres of the inner planets like Mercury, and it didn't have much effect on the outer planets, which stayed cold. And we've kind of realized it's not that simple. And so the latest theory is called the Big Tack, or the Grand Tack, TACK, referring to a change of direction that a sailing ship can do. And so we think that we had a whole bunch of super Earths in the early days, and then Jupiter came in, and then with its gravitational field broke them up into smaller things, and some of them coalesced back into they would have coalesced into something like a super Earth. But what happened was that Saturn came in behind Jupiter. So Saturn and Jupiter came in together, and then Saturn then pulled Jupiter out again. It is not that simple, and I'm waiting to see what people like Dr. Adrian Brown come up with from NASA in their planetary science studies. Don't know.
Yeah, and maybe that's something that our future astronomers and astronauts and space experts that are on here today may discover more as well, Dr. Carl. Another question here now. I've loved it. This is Ava, but what a great name to call up a question, Ava, which is also our acronym for this program. But Ava, again, is from Murrumbidgee, who have been very prolific in being involved in this program, as I've said before. And her question is, if hot air rises, why is space so cold?
For a great physicist, Richard Feynman, was asked, what would be the one bit of information that you would pass on to future generations if all knowledge was lost? If all knowledge was lost and you could send only one sentence back down into the future to people 100 or 1,000 or 10,000 years from now, what would that sentence be? And this is what he came up with. And this answers your question. It's in two parts with a comma in the middle. All matter is made up of atoms. That's the first part, comma. And here's the answer to your question, which, if they're too close together, they repel each other. But if they're too far apart, attract each other. Why they repel each other? That's fairly straightforward. Why they can attract each other, look up van der Waals forces. So when you have, and I'll do an experiment. You ready to do this experiment with me, Dr. Scott?
Oh, yes.
Okay, right. We're throwing you in here to do the experiment. Now, I want you to blow onto the palm of your hand with your mouth wide open and tell me if it's hot or cold.
It's warm.
Okay, now with the same mouth and the same palm of hand and the same distance, but with your lips in a tiny little hole, blow onto your hand.
Yes, it's cold.
Right. So the atoms have been compressed in your mouth. They come out and they want to get back to their natural distance. I'm being a bit, giving them human feelings. They want to get back to their natural distance. They need energy to do that. Where does the energy come from? From the surrounding atmosphere. So as you go up a mountain, The air molecules get further apart. They don't like being further apart. They need energy to do it, where they get that from the surrounding air, so the temperature goes down. That is a fairly basic Mark 101 answer to your complicated question. And the space itself has an average temperature of about 3 degrees above absolute zero. And I just love this. Did you know that you can get tardigrades, which are a little creature with 8 legs, about 1/10 of a millimetre to a millimetre long, and you can take them down to 2 degrees above absolute zero, 2, not 200, 2, and then bring them back to room temperature, and they will survive. And you can keep them on the outside of the International Space Station for a couple of weeks, and they'll survive. My God, what are these crazy creatures?
Amazing, amazing. The time has flown, Dr. Karl. We're at the end of the time we've got for this, but I'm hoping that you can stay around so that we can be involved in the next presentation with Dr. Adrian Brown. So I know you're a very busy man. So I just want to introduce Dr. Brown because he's an amazing Australian. He was originally from Melbourne and he's made all his way to Washington, D.C. as the Deputy Program Scientist for the NASA's 2020 Mars mission. But like Dr. Karl, he's got an amazing career. He's completed research in areas of Mars, astrobiology, remote sensing. He's worked in computer science, electrical engineering, very passionate about aerospace, as you might imagine. But here's an interesting thing. He's also a pilot, and he also served in the Royal Australian Navy. So he's had a very big career. In 2006, he was selected to be part of the NASA Ames Research Centre and became a research scientist, and also worked with the SETI Institute. Now, correct me if I'm wrong, SETI Institute was also about finding alien life, was part of the brief as well, Dr. Brown. I don't know if that's what you're involved with, but I have heard of the SETI program, and of course he's currently in the role. So we're very lucky to have Dr. Brown here. But Dr. Brown, we're just going to go on a little tangent because Dr. Karl is giving you a bit of a challenge, and he's asked about those lava vents. So before we get started, are you able to illuminate that idea about the lava tubes?
Yes, yeah, definitely. So the lava tubes are definitely probably there on the moon. We have the only evidence. The thing with a lava tube is we can't really tell by photography very easily. We have to look for openings into the lava tube that can be photographed by our orbital instruments, our cameras, and then we see something that looks a little bit like the deck of an aircraft carrier or something like that, where you have a hole in the middle of it, and you can see the shadow of the sun going into that hole. And that's the primary method we have at the moment of detecting lava tubes. And once we get things like ground penetrating radar down onto the moon, that'll be a much more effective way of mapping them underneath the surface. And that brings me the chance to mention that the rover that you see in the picture behind me has a ground penetrating radar. That's this big box right here. That's a ground penetrating radar right there. I can tell you the data that we're getting is fascinating. We're looking at beneath the surface and finding hints about the stratigraphy or the layering under the landing site. And we haven't found any lava tubes there, but we do know from the same orbital technique that there's lots of lava tubes on Mars. In particular, around Olympus Mons, there's lots of openings and caves caused by lava tubes around Olympus Mons, the biggest volcano in the solar system.
Dr. Adrian, is it true that you're very confident that there used to be water on the surface of Mars? And if so, how long ago was it found, and how did you discover that?
Absolutely. So we can answer that question in many different ways. We have discovered water on Mars many different ways, many different times. And we know that there's water in the polar regions. We've known that for as long as we've had telescopes to look at Mars. So Galileo was aware of things like that. So we've had water on Mars on the mind, but of course we haven't had liquid water as close as we have in our mission now. So on the Mars 2020 mission, we've landed right next to this amazing delta. To form a delta, you really need liquid water. And our delta is amazing. We just published a paper on it, in fact, in Science, about the fact that we've found huge 1 meter sized boulders in the side of this delta. And if you think of it of going to somewhere where a delta is forming here, like in the Mississippi region in the United States, or in the Egyptian delta, then to think about seeing a 1 meter boulder go by you, that's a big flood that has to be happening to move that much material around. So this has really transformed our understanding of this particular delta, and this is only by looking at it with our remote sensing images at the moment, and we're going to see amazing more detail when we get up close to it.
So I imagine you call it a delta because it looks like a pyramid, and that's the Greek symbol for delta. How big, so the river comes down towards the ocean and it spreads out. How big are river deltas on Earth, and how big is it? You say you're on a river delta that used to exist in the past. How big is it across? Is it like 100 meters or 100 kilometers, or what sort of scale?
So the delta that we have on Mars 2020 is we're in a crater called Jezero crater, and the crater is about 40 kilometers across.
Wow.
And then the delta fills up just a little corner of it. In fact, at the moment, from what we can see, it's about 10 kilometers across, but it may have filled more area inside the crater and then been eroded back over time, because we know from looking at the numbers of craters that landed on top of the delta, and there's a big 1 kilometer across crater in the middle of it. So we know that it's a really ancient crater, and we estimate that it's maybe around 4 billion years old. But we want to get a better number. We're scientists, and that's going to be a big focus of our mission, is collecting samples from the delta and many samples from the delta to really tie down a really good data on that delta and try to put corners on the end of when this water event was happening. How long was the water present for? How long did it take to form the delta? Those questions are going to be stunningly interesting for the geomorphology types of our planetary science community.
Dr. Brown, you've got some imagery of that, I believe, in your for your slide presentation. Do you want to throw up a couple of those slides and explain? And you said about the samples too. I think you've got some imagery there of how those samples were taken.
Yes, I do. Let me just scroll through here to the delta section. So this is our recent paper in Science, where we're looking at what we term the flood deposits. So it wasn't just a normal delta event. We were talking about flood deposits, and they came from this image of this particular feature, which is actually just a little bit, it's offshoot of the delta. It's actually on the delta itself. It's a little closer to us, and we were able to photograph it in stunning fashion, and you can see the layers inside of it. And in those layers, we resolved the meter-sized boulders. So
excuse me, Dr. Brown.
These layers here.
There's an image right in front of your image that we're seeing coming through. I don't know. It says warning. Are you able to remove that?
Hold on. Yeah. Let me see.
It's still on there. Yeah. There's a thing that says don't warn me when I open this presentation.
This image may look different. Here's a list of what changed. So if you hit the button at the top left and activate it, it might go away. It's still sitting there in the front. Yeah, that one there.
That help?
That's it. Perfect. Yes.
Sorry, that's
that's a stunning image too.
Yeah, go full screen.
So this is the let me just zoom in on this bad boy here. So you can see these layers, and these images were taken by our Mastcam Z. In particular, the Mastcam Z is on the mast of the rover. And in particular, in here, we're interpreting these things as the boulders in this Kodiak. We call this offshoot Kodiak. And of the delta, this is, well, the delta is going to be even more exciting when we get to that. And potentially will show, you know, maybe we won't find as many boulders, and that will show us some interesting variations in the water flows into the water system of the Jezero crater. And so I also should point out, you asked about how we're sure that, Dr. Carla, we've got water, we had water on Mars when this was forming. Well, so the delta has to have liquid water. It can't be ice or anything like that. It has to have liquid water, because how the delta is formed is that it has an inflow channel into the crater. And the channel actually slows down the water. And as it pours out into the exposure, it sort of spreads itself out and forms this huge deposit. So to form that delta, you need the water you need to have the water in a lake form to slow down the river, and have the river pump the sediments into the lake, and then slow down and form this delta as the water is slowed down and it can no longer hold those sediments, has to drop them out onto the floor of the crater. And that's how this feature formed. So we know that there wasn't just water, but there was a lake there. And so we've known that lake has been there since about 2005. This was identified by the Mars orbiting camera on the Mars Global Surveyor. This delta was first recognized, but now we know so much more about it by visiting it. And we're going to learn so much more when we get the samples back. And those samples will be coming back in about 2030. So for any young planetary scientists out there, you may get a chance to be the first to crack these samples open and analyze them in your lab. It'll be an international effort to analyze these data, just like the lunar samples from the Apollo region. Apollo times have fueled our knowledge of the moon. We expect that these will do the same thing for Mars.
Wow.
You mentioned about the samples.
Let me just show you the Mars sample return aspect of this this mission. So tell me if this is working. So,
yep,
okay.
You're full screen.
Great. So this is the first, so I'm going to make a small admission here. And our first sample, we actually made a mistake as a team. Everything is doing really, really well with the rover, and we were feeling really good about the landing, and everything was working perfectly. But then when we first went to a site where we tried to get a sample out of the ground, we didn't understand how friable, how soft and easy to break the rocks would be. And so what we think happened is we drilled just like they do in the JPL lab, because they have a copy of this rover in the JPL lab. And so they did tests on terrestrial rocks in terrestrial environments, that is on the Earth in Pasadena in California. And so they had a model for how the rocks should perform, how hard they should be. And unfortunately, the first Martian rock we drilled into more or less fell apart, unfortunately. And we unfortunately only found out when the sample was loaded into the rover and imaged, and there was nothing there. So this is our actual first successful sample taken. In this image, this is a sort of a selfie of the rover after the dual samples were taken, because we're going after dual samples because you can learn so much more when you've got two tubes of pretty much the same material. It's very valuable to have those. So those were taken on that rock there, which is called Rochette. You can see that down the bottom of the screen. And the rover is very proud of itself for taking those samples. And just to give you some idea, we put a lot of planning into the so-called model or baseline mission. We had ideas about how many samples we take of each of these different types of rocks that we could see from orbit. And then now we've sort of screwed that up a little bit with our first sample. But we're calling it, instead of calling it a failed sample, we call it the atmospheric sample. So so that's us for ingenuity, shall we say. And I'll just show this quick video, and this actually will give you an idea of, we went through this process with our first sample, and the drill goes in, and at this point we think that we lost the rock just there as it was coming up. And now we've designed into the next, let me see that again. I just want to show you that. Okay, maybe we won't get that. Let's see. All right. So we've added into this a check from the mast instruments for the rover, which happens just about here. So here, this is where the sample is going up to the sample tube to enter the rover, where it's stored on board the rover. And then at that point there, we have the opportunity to add in an extra sequence of images from the mast. You can see the mast unit in the background there. So the mast will be looking down at this. And actually, we did that for the first time with our successful samples that you just saw. And we checked before it went into the rover and used up the tube. And so when it goes into the rover, what happens? It's rotated around into the body of the rover. That's about the size of your big finger, and it's made of titanium. So the sample is checked and it's imaged at this point here, and this is where we realize our failure to collect any sample in the first instance. When we measured the volume and sealed the sample tube and image, we saw only a little bit of dust in the bottom. And then this the rover then transfers it to the back of the rover, and it's put into these canisters here. And each of the sample tubes has a canister. Those canisters can then be jettisoned at any time. We haven't done this step yet, but the idea is that you move this arm out of the way and then jettison these canisters one at a time. Then they drop onto the surface. And what's that for? Well, that is because the Mars sample return mission will have a microwave-sized rover that'll sidle up to these samples on the ground and pick them up with its hand. It's got a big arm. Basically, that's all it's got. It's a microwave with an arm. And it's not as complex as Perseverance, but it'll be able to go back into the sample return vehicle, which will then ascend up into the Martian atmosphere and escape from Martian gravity and go back to Earth with the samples it's collected. So we have a lot of flexibility on this sample return, but at the moment we just have these 3 tubes sealed and ready to go. But we're working this weekend actually on our next 2 samples.
Dr. Brown, we've got about 3 minutes to go. There's a lot of interest in the little drone. Are you able to tell us a little bit more about the drone that's the partner for this project?
Yes. So let me just.
Yeah, and how does it fly when the atmosphere is less than 1% of the Earth's atmosphere? How do you guys do that? Tell me.
Yes. So so the drone is called Ingenuity, and it's a very light a drone that it revs the rovers, it revs the rotors that it has at 2,800 RPM. In fact, we're planning to have the rover. This is the deployment of the Ingenuity onto the ground, onto the surface. And I should point out that at each point when each of these images were taken, the helicopter engineers looked at the image to check every time every deployment stop had happened because they were very worried about things going wrong in here. But fortunately, everything worked well. We got this fantastic first selfie. You can see this was taken when the rover hadn't got much dust on the surface of it on the top of our on the rover. But then we took this selfie of Ingenuity, successfully deployed, and we were thinking that it would take 5 flights. It's now up to flight 14, and it basically it plays a game of catch up because it can't go too far away. Just like your drone in the backyard in Australia, you don't want to send it over to the neighbor's place, particularly if you've got a big backyard. You'll lose your remote control signal, and so we don't want to do that. And so essentially it plays a catch up every 20 sols or so, or depending on how far the rover is moving. We haven't been moving much for the last little while because we're in a very interesting scientific area. But essentially we just give it commands to go a little bit further on and catch us up. And, that's how it's got to 14 flights. And I'm particularly very interested in the fact that it'll probably be able to get very close to the Delta deposits as well. So that'll be very fascinating as we were sidling along the Delta.
Is it nuclear powered like the rover, or where does it get its power from for its flights?
So it's a solar powered helicopter. So there's solar on top of the. Let me see if we've got it. You can sort of see the solar panel on top of the helicopter there. And it actually has 2 cameras, essentially the same as your iPhone cameras. It has a color and a black and white camera here. And basically the solar power is used by the helicopter. So, and essentially it's self-cleaning as well. So we don't have any problems with too much dust collecting. After you do a flight, it's all clean. And I do want to mention one thing, because you asked about how the helicopter is working at the moment, and in fact at the moment it's getting colder at our landing site because we're getting through summer, and what happens on Mars is that during winter the air actually thins out. Now that's different to Earth, as you'll be able to recall for us, Dr. Carl. So in the Earth we have. If you're a pilot, you'll be used to flying in heavier air or thicker air, higher pressure air during winter. But that situation is reversed on Mars, because what's happening during winter is the polar cap is getting all of its material deposited onto it. It has CO2 ice, and all the CO2 in the atmosphere is getting trapped out into that polar cap. So during the winter conditions, the air is getting thinner. So the engineers on the helicopter team have designed a model for this, and they're actually ramping up the rate of the rotation of the helicopter to try and keep the performance of the vehicle about the same rate, about the same nominal response as it gets colder.
Now here's a weird thought. Would it be possible, if you get dust on the lens of the cameras on the rover itself, would it be possible to use Ingenuity's air blast to clean them?
Yes. Well, I mean, it's not impossible, but I will tell you that at NASA we're very careful about how close the helicopter can go to the rover. So we're never giving the rover any commands to fly over the rover on the off chance that it's going to fail and collect the rover. So we're quite risk averse in that regard, and so the rover we even have a keep out zone, a little bit like an airport or a city or something like that. So you've got to stay away from the helicopter. So we tell the helicopter team, come up with your plans, but make sure you don't go close to the rover. But we do have you mentioned the chance of dust getting into, say, the optics and stuff like that. So to get around that problem, the biggest dust problem was when the rover landed on the surface. So as we were landing, all of this material was kicked up. And basically, let me just show you that video here, because it's quite graphic, to give you an idea of what was happening.
This is
Let me
amazing,
know if you're seeing it.
Adrian. As we look at this video, definitely play it. But thank you for showing. So think about the ingenuity of the ingenuity. It is fantastic. And considering the ingenuity the students have been putting in with their school projects, and we've been able to see a bunch of these projects been sent in, and we're really keen to do a bit of a share. But I must say, this has been fantastic, Adrian. Really, thank you so much. And Carl, love your taking us into the danger zone in 1% atmosphere. Why not? Fantastic.
Yeah. So this is our landing sequence, and you can see the rover here going into this dust bowl, if you will. So that dust bowl, to get around the fact, to get around the chance of us getting any dust into our optics or anything like that, the actual mast was not deployed at this time. So the mast isn't deployed until after the landing has happened, and everybody's really super happy. Let's
Wow.
see that again.
That is awesome.
So, well, thank you very much, Dr. Carl and Dr. Brown, for that. That was absolutely fascinating. We could talk for hours, and maybe in the future we might get you back to talk about where the program is going. But I'm going to jump over to Ben, who's going to move into the next section, and I think Dr. Carl and Dr. Brown are going to be involved in that as well.
100%. And also Alan Ryan, as well as Ted Tagami, who people will remember from magnitude.io. Kylie and Glenn have been sort of thinking about iterating school design and seeing some of the designs that we've been seeing, and it's just amazing. So Kylie and Glenn, I'd love to see what you got to share for us today.
Fantastic. Well, given the expertise and the discussion so far, it's really exciting to be able to link these concepts to the big ideas that are coming out of the classroom as part of the AVA Challenge. So Glennie D is going to just review some of the images that we're seeing in designs in moving forward. Once we have a better understanding of the atmospheric conditions on Mars, what we might be proposing to do in terms of establishing colonies and life and plant production. So can we have a look at some of the images that have been coming out of our schools in regards to this? Okay.
Thanks, Miss B. We have some, hello to everyone. Thank you again for joining in, and our amazing panelists. Remember that they and we all turn up for you because we believe that you will have an amazing career and can do amazing things. So I just wanted to show you quickly something that was sent in from some budding off-Earth engineers down at Rayton in Victoria. And the Year 5 girls have been working on underground structures. So all of these are a side view or a section view, a cutaway. So for instance, Alice's drawing, you can see a ground line just underneath the plants and everything else is underground. And Beatrix, let's go over to number 1. Beatrix, I can see just under the double domes, she has carefully thought about how the plants will be processed, how the harvest will be processed on the belts and where they'll be stored, and all of the systems that are going to be needed, Miss B, to maintain all of that. Like, incredible. I want Beatrix, Alex, Coco, Olivia and Erin on my team if I'm building off-world structures. Thanks, girls, for sending that in.
Yeah, it's absolutely fabulous. The level of detail and the systems and the thinking behind that. Now, what we're going to do is we're going to ask our panelists now in a really quick round is how do these design concepts translate to what they're finding in real time in their experiences with the International Space Station, their work with NASA and the Mars rover, and also some Dr. Carl insights into his wealth of knowledge. So what I'm going to bring up now is some of those big ideas that have facilitated these drawings. So Jackie, are we able to? Fantastic. And I'm going to ask the panel, first of all, I think a great place to start would be just looking at the concepts that have come here about creating a dome to sustain life, which is really important. We know that there's water on Mars, and we're also looking at establishing colonies on the moon. What is the likelihood that we would be able to use the physical landforms, Dr. Brown, that are already on the moon, like the delta? Like, how stable is it so that we would be able to anchor some of these design ideas, like a dome or filling an existing crater with water by melting ice so it can become an ecosystem? What is the stability?
Thanks very much, Carly, for that question. So, as I was mentioning during that intro section, we thought we had a good model for how hard rocks were at our landing site. We were using terrestrial models, terrestrial lavas and stuff like that. But then when we've been doing our drilling into the rocks there, we've managed now to find that they're actually sometimes softer than any of the rocks that we see here on Earth. So that's something that we're learning right now, and something that you'll be able to use for those for these habitats. And you have to have a way of, for example, not relying on the rocks. So not potentially not building something that's on top of that delta or something like that, without something some big trusses down below this to potentially hold up the habitat, for example.
There's a lot of validity,
good
really.
Good idea.
Yeah, having the underground elements that the students was just drawing. And how does that go, Ted, when we're looking at plant life? So brainstorming around these big ideas. So we understand that there's some limitations in terms of the physical structures, but then what does that mean in terms of being able to create habitats for plant life?
Oh, yeah, I think Dr. Adrian Brown definitely began talking about it with respect to looking for water ice at the Delta. There's another big challenge in addition to the water for our plants. Of course, we'll need that, is the sunlight. You have about 45% or so of the sunlight reaching Mars as it reaches Earth. So you've got a lot less light. So that's a challenge, but also the dust and dirt that represent the Martian planet surface is full of salt. And as a little experiment at home, I wouldn't do this in your garden, maybe a little potted area. Get 2 pots, have soil in one and have soil with a little salt in the other. Tell me what happens to that second plant. I don't think the outcome is something you'd like. Salt perchlorates in the soil are going to be a big challenge if you want to try to mix it up and grow your plants. I like those illustrations. Makes me begin imagining how we might be able to develop a future habitat on that planet.
Yeah, and certainly a lot of adaptations that plants go through to be able to accommodate different levels of salt. So that's really interesting. So the question is, Dr. Karl, as we're brainstorming these big ideas, is it going to be that we're able to adapt to Mars and the different space environments like on the moon? Or are we going to have to just drop modular units and hope for the best? So what do you think at the moment is more likely in terms of an outcome?
I think we're off to a really good start. And you've got to say A before you can say B. And along the way, you'll make mistakes. And it was very interesting, both what Adrian was saying about the structural integrity of the soil, which could range anything from blast-grade concrete down to wet sand, and also what Ted was saying about the salt. Now, just a little diversion. Back in the old days, a couple of thousand years ago, when the Romans wanted to be really mean to somebody, not only would they destroy their civilization and kill everybody, they would then go to the trouble of getting this really expensive stuff called salt. And it was expensive then because we get the word salary from salt. Literally, some of these soldiers would be paid in salt as their income, as their pay. And they would get this very expensive stuff called salt and then run it across the fields of the country that they're trying to wipe out so that nothing would ever grow again. So what Ted's talking about there is really clever. And then you can go to the next stage of realizing the mechanical and biological limitations and think, how can we work about it? Hooray, biology. So it turns out that a few years ago, 2 female scientists won the Nobel Prize for discovering a tool for genetic engineering called CRISPR, where you basically just sort of shift things around in the DNA and you can make people shorter or taller, or get a Rottweiler over a few months to mutate while it's still alive, say into a Chihuahua. We can't do that now. But I'm sensing We're going to need, besides the massive mechanical engineering and the biology, we're going to need the genetics to help us modify the plants so they can grow in the soil, and then us so that we can survive there. So like our current design, like 2 legs, mate, you fall over. I'd like 3 legs, and the brain out in the stick, I'd like it buried in the center of the body. And I'd like to be able to go out on Mars without a spacesuit. We can't get there now, but consider the difference between 100 years ago and now. So biology and genetics will be a big part of our push as we go towards colonization.
Yeah, what a fascinating blend between, you know, what we know now and our knowledge, and how through processes like the CRISPR we can actually like change DNA structures for adaptation. So it's just so fascinating, such a broad area of expertise. So how do we pull it all together? Alan, so we're so interested in this as a project, but the reality is that a lot of it has to be mastered on Earth, and it's a very diverse transdisciplinary team. And I know that you're an expert in project management. So what advice would you give to the students as they're trying to manage these big ideas into an outcome for their projects?
Oh, thank you, Kylie. That's great. What I love about the presentation so far is that we've had the big picture view of going to Mars and the rover, and we've also had the small picture view of worrying about the dust on the lens of the camera and how to actually organise and change that. So when you're doing a project, you have to think of the big picture view of all your great ideas and all your great pictures and how you bring it all together. And then you also have to think of the small picture view of how do I actually deliver it on time? Am I delivering what's required by the challenge? Am I doing what's required by my teacher? So I just want to share with you just 2 little thoughts. Can I ask to share the screen, thanks? So firstly, I'm from the Hargraves Institute, if you can see that. And we're named after Lawrence Hargrave, who was the world's first flyer without hot air in 1893. So Australians have been doing wonderful things for a long time. But what I want to focus you on as all students is just 2 simple things. Is you just need to take a step back right now, pause and reflect. And this is when we learn, when we pause and reflect is when we learn, and just evaluate how your project is going right now, and then iterate to make it better. So evaluate and iterate. And so are you happy with your project? How is your team feeling and your teacher feeling? Right? Does your solution actually answer the problems in the challenge? Right? Are you following a plan? These are the things that you use to evaluate your project rather than the content of it. How can you improve your project? Can it be revised in time to meet the deadline? And we always have to meet the deadline. And what's important to be finished by the deadline? So now's the time to come back to Earth and look at the moon, and come back and look at your project and evaluate and iterate to actually have a better project. So thank you.
Wow.
Thank you. It's amazing to actually see these projects and the actual work that's coming out of the classroom. The curiosity and the actual real science that is, influencing their decisions is really powerful. Dr. Brown, Dr. Carl, thank you very much. And Ted Tagami, really appreciate that insight. Back to Ben now for a final wrap, I think, before we look at the folio.
Sure, no worries. Wendy, we really are with week 5, the folio. Let's get into it.
Oh, let's get into this folio, Ben, definitely. So last week, we looked at designing with Glenn and Kylie, the sketching, and we also talked about computer-aided design tools with Ian, and he talked to us about Tinkercad and SketchUp Pro. I kind of talked a little bit about how to train like an astronaut with developing your core muscles using the plank exercise. But this week we are definitely going into our evaluating the prototype, and I'll just pass over to Mr. Preston.
Thanks, Wendy. We've got once again a great folio for the students and the staff out there to work through this week. The folios have been a highlight, I think, as well of the AVA challenge that's been put out. Jackie, can we go to the page that shows the iSTEM engineering process? This was on page 4 of week 1 of the folio. So you'll see there we started way back in week 1 with defining the problem that we had. This week, week 5, we're actually looking at 3 of those cogs. So we're looking down the bottom at cog 5, which is prototyping, cog 6, which is evaluate, and cog 7, which is iterate, which is what Alan spoke about the last few minutes as well. If we go back, Jackie, to page 48 of this week's slide, and we'll bring that one up quickly. So a prototype is where you go and make the object, and we're going to see whether or not it actually functions the way that you hoped it would function. We also that allows us to empathise with our audience, perhaps. So if we're making a mobility aid for someone who was disabled and we go and actually try that ourselves, we might empathise with what the issues are that they're trying to overcome. Jackie, we also have a slide of the Space Shuttle Atlantis. If we can just throw that one up really quickly. And I mentioned a few weeks ago, I was lucky enough to go to the Kennedy Space Center in Florida and actually see the Space Shuttle Atlantis. And when I was there, the guide was telling me that NASA also obviously has to do prototypes and evaluate and iterate. And the guide was telling me that the heat shields on the Space Shuttle Atlantis, the first space shuttles, not the Atlantis, but the first space shuttles, they performed a suction test. And the idea of the heat shields is that protects the aircraft, particularly on re-entry, because it gets so hot. And they did a suction test, which really basically is like putting a vacuum cleaner onto the tiles to see that the glue adhered to the craft. And they found that several of them fell off, and that put the program back, enormously, about 12, 18 months in time. So the students, you're at that stage now of prototyping, testing, evaluating. You may not get it right the first time. NASA doesn't get it right the first time. Main thing is to do your best. Wendy, I'm going to throw to you now for page 49.
49, definitely. Now, this is how you can evaluate your prototype. There are many, many different tools that you can use. I really like the PMI tool though. So this is where you're going to write down all the plus attributes of your prototype. So write down all of the good things about your design. Then in the minus section, you need to think about, well, what didn't actually perform as well as you thought it was going to be? And then the last part is interesting. So what are some of those observations that, they don't fit into the plus and they don't fit into the minus, but they're interesting? And this is the part where you then continue to change your design to make it better. Over to you, Mr. Preston.
Okay, thanks, Wendy. So that takes us to page 50 of our folio, which is our iterate. So to iterate is to come up with improved versions of what we're looking at doing. Jackie, I believe we have an AHA slide, a question for our students today. If we can bring that one up really quickly. I did see a great thing, a great show on TV last week about James Dyson, the man who invented the Dyson vacuum cleaner. And I was absolutely astounded to hear that it took him over 5,000 iterations to get to, the perfectly functioning bagless vacuum. I've got a question up here, and Edison, the inventor of the light bulb, the question is, how many times do you think Edison had to iterate before he had success? And Jackie, what are our options there? Because I can't see them on my screen. I can see them now. So our options are, do you think Edison had to iterate less than 10 times, between 11 and 100 times, between 101 and 1,000 times, or more than 1,000 times? Okay, so that's our question on our poll this week, and I see the results are starting to come through there. I'm very happy to see that there's no for less than 10, and I'm not going to tell you what the actual number was. You can find that out for yourself, but if you're on that far right-hand column, which is a nice sort of pinky color on my screen, I think you're well and truly in the right area. So, Wendy, back over to you.
Thanks, Ian. So in the first week of Train Like an Astronaut, we worked on our strength and coordination through burpees. And last week, we worked on our core muscles through planks. Today, the skill is about agility. So if you have Surf Lifesaving Club in your community, you would understand this one, but you lie down on the ground facing the opposite direction to where you've set up cones in a line. And then when someone says go, you jump up and you have to weave your way through the cones. And the first person at the end is the winner. So we would like you this week to set up an Astro Agility course. And then in your folio, it actually gives you some options of how to make that more difficult so that you can build your agility skills. So that's what training like an astronaut is like this week. Over to you now, Ben.
Absolutely. I hope you are training like an astronaut. Remember, we challenged you to see if you could do some training to reduce your heart rate. How are you going with that? So look, hey, thank you so much. What a really awesome session. I know this has gone a couple of minutes over, but that was the point we wanted to go. This is what's happening up on Mars all the way through to what's happening in schools. So I'd love everyone who's been involved in this particular session to unmute your videos, because it's always nice to say hi to everyone. And sadly, say goodbye, because next week it is all about communication. Communicating what we're doing, our pitch and more. So look, thank you so much. We cannot wait to hang out with you again. Dr. Carl, Dr. Brown, Ted Tagami, and all the team. Thank you so much, Alan. Enjoy your day. All the best. This is going to self-destruct. Hope your rockets don't. In 5, 4, 3, 2, 1.